All right. Before we get into Riemann sums here, after doing left, right, and midpoint rectangles, you're going to need to be able to write these things a little more efficiently. If you don't know sigma notation, here we go. By the end of this, hopefully you can represent sums in sigma notation. You might also call that summation notation. Both are good to go. Okay. Here's what this looks like. That's a Greek letter sigma. And this is read as the sum, right? This big part, that Greek letter sigma, indicates we're going to add a whole bunch of things together. So when we see that, we're going to say the sum. Okay, so the sum, maybe I should write this out. The sum from k equals 1 to 10, and that k equals 1 is the same kind of thing as the top number. 1 is the first index, 10 is the last index that are substituted in. So again, we read this as the sum from k equals 1 to 10 of k. Meaning, it's actually pretty straightforward. We put 1 into k, and then we put the next integer into k2, and the next integer into k3, the next integer into k4. You get the idea. And the last number we put into k is 10. And this adds up to 55. You can easily see that because 1 plus 10 is 11, 2 plus 9 is 11, 3 plus 8 is 11, and there would be 5 of those pairs. I should probably do a video on that. Okay, so how would we read this? We would read this as the sum from k equals 6 to 10 of k. And the reason I like to put this in here quickly or first is, the last example, depending on how you were taught, a lot of times people think that that upper 10 index is how many terms. Well, that's true if you're starting at a lower index of 1, but something else like this, we're obviously not starting with an index of 1, we're starting with 6. So that's 6 plus 7 plus 8, how about a plus 9 plus 10. Okay, and that's clearly not 10 terms, that's 5 terms. Okay. So how do we read this? The sum from k equals 1 to 10 of 3k. And, well, now you can see that that stuff inside the sigma here, that 3k is like a formula. So the first term is 3 times 1. And I could write 3, but maybe it's better to write it this way. 3 times 2, 3 times 3, 3 times 4, all the way up to, well, the last one is going to be 3 times 10, and the penultimate term is 3 times 9. And so that works, and we could add all that up, but something else you should know is obviously we could factor out that 3, and we'd be left with, something we already wrote. I already wrote. How about that? Okay, and what that means is, this original thing, instead of writing the sum from k equals 1 to 10 of 3k, that's identical to 3 times the sum from k equals 1 to 10 of just plain old k. Said another way, you can take out, just like we did with derivatives, limits, almost everything, you can take out, or I don't really like factor is the right word, but whatever. You can bring out any constant multiplier. So that's kind of cool. We may need to do that once we get to Riemann sums. All right, so now we know what this means. All right, we just wrote that out, and that's 3 times 1 plus 2 plus 3, skip a few, plus 9 plus 10. And we just went through y. That's the same as the previous version. Okay. I throw this one in just because I know, I don't know, maybe it's too easy, maybe it's too hard. Okay, so this is clearly, there's no place to put a 1 in for a k, so it's 2 plus 2 plus 2 plus 2, and I know my kids are going to skip a few, 2 plus 2. Well, unlike the last few, we really can't shorten that up because it's not clear since, I mean, I guess 2, 2, 2, 2, 2 is a pattern, but it's not a pattern that's countable without knowing the terms the way these other things are. So I suppose we have to write out 10 twos, or we could just think through, this is going to be 20. Gosh darn it, it says expand, so we're just going to have to write out 10 twos all added together. 8? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, cool. Let's see if you can go in the other direction. So 2, 4, 6, 8, and obviously 10, 12, all the way up 18 to 20. And let's think through this. So we know we're adding up a whole bunch of things, and there are two good ways to go. We'll go, well, I don't know which way first. Let's leave the top thing open. I'm guessing at least one person says we're going to start at 2 and go to 20 to get this. But the problem with that is, if we put a k here, what this is equal to is 2 plus 3 plus 4 plus 5. The index always increases by 1. So that's not going to work. We're going to have to try something else. Okay? And that something else, we do need to, well, I guess we could start with an index of 0. That's pretty common. But let's start with an index of 1, and let's think, how could we get 2? And the answer is, well, we could write 2k. And then notice that's going to be 2 times 1, which is 2, plus 2 times the next input, 2, plus 2 times, I'm sorry, I said the next input. I should say like the next integer, the next whole number. 2 times 3, and that's going to go all the way down the line. So that seems right. And then writing out the first few really tells us, well, how are we going to get to 20? Well, that's going to be the 10th term. 2 times 10 is going to be 20. Okay, so that's how I'm going to write that. Now, hopefully you know the other way to go. If we realize something I said earlier, this is going to be the same as the sum from k equals 1 to 10 of k, and then you just multiply the whole thing by 2. Okay, so this should be nearly as easy. We see 2, 4, 6, 8, so we know it's going to be the sum from k equals 1 to something of 2k. And we just have to think through, well, if I'm doubling, what's my upper index? Well, I'm doubling every single one, so I would have to double 50 in order to get 100 as the final term. Okay, I think this is pretty good. And in fact, this one, 1, 2, 3, oh, that's actually pretty good. So since these are counting by ones, I'm going to have a single k in here, and that's also pretty easy to tell that the upper bound is 100. That's all. I hope it helps.